Hello. We'd like to tell you about our work, Rethinking Sim2Real. Lower fidelity simulation leads to higher Sim2Real transfer in navigation. The last few years have seen significant investments in the development of new simulators, curation and annotation of 3D scans and assets, and development of techniques for overcoming the Sim2Real gap. However, no simulator is a perfect replica of reality. The default operating hypothesis in Sim2Real is that increasing simulator fidelity reduces the Sim2Real gap. As such, we ask, can Sim2Real transfer be improved by decreasing simulation fidelity? In this work, we show that the answer is yes. We focus on the task of visual point goal navigation in unknown environments. In this task, a robot must navigate from a starting location to a goal location without access to a map. The robot has access to an egocentric depth image and a GPS and compass sensor for localization. In this work, we focus on point goal navigation with legged robots. When training our navigation policies, we use two levels of physics fidelity, kinematic and dynamic. Kinematic simulation uses abstracted physics and teleports the robot to the next state using Euler integration. Kinematic policies command robot center of mass, linear, and angular velocities. Dynamic simulation consists of rigid body mechanics and simulates contact dynamics. Dynamic policies command center of mass, linear, and angular velocities, which are converted to robot joint torques by a low-level controller operating at 240 Hz. We evaluate the kinematic and dynamic policies on a spot robot in the novel lab environment. Here we show rollouts for 5 different episodes in the real world. All kinematic policies achieve a high success rate of 100%. Additionally, kinematic policies trained in Habitat take an average of 26.4 actions and collide 3.1 times. On the other hand, the success rate drops to 40 to 67% for the dynamic policies. On average, a dynamic policy trained in Habitat took 107.9 actions and collided 41.2 times. We evaluate our hypothesis using 3 different robots, Spot, A1, and Alien Go, and 2 simulators, Habitat and Gibson. We train policies using 2 physics fidelities, dynamic and kinematic. We study the combinatorial space of experiments, policies trained under 2 training conditions, kinematic and dynamic, 2 evaluation conditions, kinematic and dynamic, 2 simulators, Habitat and Gibson, and 3 robots, Alien Go, Spot, and A1. If we look at the kinematically trained policies in the left column, we can see that they outperform the dynamically trained policies in the right column in terms of success rate. This holds true even when kinematic policies are evaluated in a dynamic environment, as shown in the lower left quadrant. These relationships hold true for all 3 robots. We plot the evaluation performance of both policies in Habitat kinematic and dynamic simulation.
While both kinematic and dynamic policies are trained to convergence over 3 and 7 days respectively on 8 GPUs, we see that kinematic training is much faster. With kinematic training, the robot is able to learn from approximately 10 times more experience.
This increased experience allows the kinematic policies to learn intelligent, high-level reasoning. In this paper, we propose the counterintuitive idea that higher fidelity simulation does not necessarily equate to higher success. We also find that dynamic policies have a tendency to overfit to the simulation physics and do not generalize well to the real world. Our findings suggest that instead of investing in higher fidelity physics, the field of Sim2Real should prioritize simulation speed. Thank you for watching.